In this lesson, we're going to take a look at a second definition of a derivative of a function that builds on the one we have been using up to this point. We'll begin by taking a look at these two different derivative definitions, the one we've been using already and the one we're going to introduce now. And then we'll turn to some examples in which we use the second definition to find the derivative of a function. Let's begin by taking a look at our two derivative definitions. Recall our first derivative definition. We said that if we have a function f of x, we can define its derivative f prime of x as this limit, the limit as h approaches 0 of f of x plus h minus f of x over h. The expression inside the limit, which we call a difference quotient, represents the slope of a secant line going between 2 points on the graph of f, where h is the horizontal distance between those 2 points. And when we take the limit and let h approach 0, that means that we shrink that horizontal distance between the points smaller and smaller until the points are so close together that we, in effect, cannot tell them apart. And when that happens, the secant line that we start with becomes indistinguishable from the tangent line whose slope we're trying to find. That's what a derivative ultimately gives us. That definition is great, but it comes with some challenges. In particular, if we want to use it to find the derivative of a function, we often have to do some fairly complicated algebra. And that often comes up because of the expression f of x plus h that appears in the definition. In at least some contexts, a sum like x plus h tends to produce some complicated algebra. An example is when we're working with roots. If we have something like the square root of x plus h, that can be a little difficult to work with because we don't really have any convenient formulas for working with sums inside square roots. The same thing comes up when you have, say, a fraction with a sum in its denominator, something like 2 over x plus h. Right? There's not really a good way to break that up in a way that makes it easier to work with. So the second version of a derivative definition that we're going to take a look at now avoids these problems because the x plus h part of the definition we've been using does not appear in this other definition. Let's take a look at that second definition. To see how this works, go back to our starting point for finding a derivative, a secant line between 2 points on the graph of a function. So here's a diagram illustrating this once more with our secant line in red. Our goal is ultimately to find the slope of the tangent line at A, which isn't drawn here, but it would be the line going through the point A, f of A, and touching the blue graph at exactly that one point and nowhere else. So we've seen that to do this, we need to bring the other point, B, f of B, closer and closer to A, f of A. One way to do this, a way that's slightly different from what we've been doing up to this point, is to let the value of B get closer and closer to the value of A. So that leads us to our second definition of a derivative. So this will be a definition of f prime of A, the derivative of a function f at the point where x equals A. It looks like this. It's the limit as x approaches A of f of x minus f of A over x minus A. Now here we have x, which is a variable, and it plays the role of the x coordinate of the point we are moving closer and closer to the fixed point that we're working with. So this is what we were calling B earlier, but now since we're changing it, we'll use x instead. And then A is the x coordinate of the point where we want the tangent line or the slope of the tangent line. So A here will be a constant. And typically when we work with this, we will let A be a particular constant, and then we will end up with the numerical slope of the tangent line at the point in question. Or if we want, we can continue to treat A as a kind of variable, and then that will give us a formula for the derivative of f at any value of A. Let's take a look at some examples that involve finding a derivative by using the second definition. Here's the first one we'll take a look at. We're going to find the derivative of 1 over x squared at -1. Or more precisely, we can say that we're going to find f prime of -1, given that f of x equals 1 over x squared. So using our new definition, we can express the derivative like this. We have the limit as x approaches -1 of 1 over x squared minus 1 over -1 squared over x minus -1. Here, if you go back to that definition we had earlier, the general definition, we're letting a be -1, and wherever we have f of x or f of a or anything like that, we're replacing it with 1 over x squared, or a value of that function. We'll now work on this limit using simplification like usual. To start, we can clean up the arithmetic a little bit. Rather than having 1 over -1 squared, we can just write 1. And where we have x minus -1 in the denominator, we can rewrite that as x plus 1 to make it a little easier to read. And now if we get a common denominator in the numerator, common denominator of x squared, we end up with this. Notice that this is a much simpler common denominator than when we saw a similar example of this using our first definition of a derivative in a previous lesson. At this point, we can simplify the complex fraction. Rather than dividing by x plus 1, we'll multiply by 1 over x plus 1. And then we can factor the numerator. It's a difference of squares that can be factored into 1 minus x times 1 plus x. And notice that we now have a common factor, 1 plus x or x plus 1. They're equivalent because of the commutative property of addition, and we can cancel it. We're left then with this limit. The limit as x approaches -1 of 1 minus x over x squared, and we can find that limit by substitution. Substitute -1 for x, and evaluate what you get, you will obtain 2. So the value of f prime of -1 here is 2. This still involved a little bit of complicated algebra with a complex fraction, but it was still simpler than if we had done this using our initial derivative definition, using the f of x plus h term instead of the one we used here. Let's modify our example slightly. What if we want the general derivative of 1 over x squared rather than the derivative of this function at a particular value of x? So what we can do is to adjust our example so that we obtain the derivative of 1 over x squared at any point a, or any point where x equals a. This is now the limit we need to work with. The limit as x approaches a of 1 over x squared minus 1 over a squared over x minus a. This is exactly what we worked with before, but with a in place of -1. The steps involved are exactly the same as our previous example. We'll get a common denominator in the numerator in order to subtract. We'll then factor a squared minus x squared and move x minus a into the main denominator of our expression. So we end up with this here. Now at this point, we're going to use a little algebra trick. We cannot cancel a minus x and x minus a. They are not the same factor. They're similar, but the order of the terms is reversed, and when we have subtraction, that matters. But we can cancel them as long as we leave behind a factor of -1, here just showing up as a negative sign. So a negative sign or a -1 factor allows us in effect to turn around a difference. And then what we have in the previous line is equivalent to what you see here. We can now substitute a for x. And with a little bit more algebra to simplify, we'll combine like terms and cancel a common factor of a, and we get -2 over a cubed. So that is f prime of a for any arbitrary value of a. You might say, well, wait a minute, that's not quite what we're trying to find. So we need to make one more minor adjustment here. We said that if f of x equals 1 over x squared, then f prime of a is -2 over a cubed. Well, that's fine. But notice that in our derivative equation here, we're using a as the independent variable or the input variable for our function f prime. But our original function used x as the independent variable. The good news here is that nothing much really matters when it comes to these letters. A here can be any value of x that we want. So in a sense, there's a little bit of redundancy. Since x can already be any value of that variable, we can replace a with x in our equation that defines our derivative, and we'll be talking about the exact same function. So what we can conclude here is that when f of x equals 1 over x squared, f prime of x equals -2 over x cubed. Let's wrap this up by taking a look at how these derivative definitions appear on the AP Calculus exam. Typically on the AP exam, you will not have to do the kind of complicated algebra that we've been doing to find derivatives of functions. And that's because pretty soon we're going to start developing formulas or shortcut rules for differentiation that will make the process of finding a function's derivative much easier and much faster. And then we won't explicitly have to rely on these limits that we're using every single time. But the AP exam will expect you to know these two definitions of a derivative. And one way in which the AP exam will test your knowledge of these, the most common way, is in multiple choice questions where they'll give you the limit in question and you will need to recognize that it is a derivative. So we're going to take a look at an example, but let me warn you here, you know what to expect from this example. You know that this example is testing your understanding of the definitions of a derivative of a function. So it's not too hard then in this example, as you'll see, to understand what to do. But when you're not really thinking in the front of your mind about definitions of the derivative, you might have a harder time remembering that you need to do this sometimes on the AP exam. So we'll continue to come back to this in future lessons in order to continue practicing recognizing these limits that define a function's derivative. But let's take a look at our example now. This is a sample AP derivative definition question. Say we want to know the value of this limit. The limit as x approaches 1 of 1 over x squared minus 1 over x minus 1. If this were to appear on the AP exam, it would probably be a multiple choice question, but we'll treat it as a free response question for right now. Of course, if there were answer choices available, the easiest way to deal with that is to solve the problem and then figure out which answer choice best matches what you obtain. So if you look at this on the AP exam, one thing you might think is, how am I supposed to evaluate that limit? That will be annoyingly difficult at the very least because it's a fairly complicated expression inside the limit. But if you recognize that that limit is a derivative of a function, it becomes much easier to figure out what this limit is. There's a clue that you're dealing with a derivative here. Notice that the thing inside the limit looks like the kind of expression we would use to evaluate the slope of a line. We usually write slopes like this, y2 minus y1 over x2 minus x1. The key thing here is the structure. We have subtraction over subtraction. And in the limit we're trying to find in our sample question here, we have subtraction over subtraction. So that suggests that we can analyze this limit as though it gives us a kind of slope. If we see that that limit is a derivative, then we can translate this question in our minds into this. Find f prime of a for some function f and some input a. And here we're working with the second definition of our of a derivative, the one we just introduced. There's the general definition here. And notice the thing in the f of x place is 1 over x squared. By the way, you can tell that we're working with the second definition of a derivative because the denominator is x minus 1. In the first definition of a derivative, we usually have just a single variable expression there like h. So if we take a look at our second derivative definition that's on the middle of the screen, and we compare it to the limit we're given in our question, you can see that a here will be whatever value x is approaching. And in this case, that is 1. We have a limit as x approaches 1. F of x appears before the minus sign in the denominator. So here that's going to be 1 over x squared. And now we can think of our problem as a matter of finding the derivative of 1 over x squared at x equals 1. So we're ready to answer the question. This is what we're trying to find. We can rewrite this now by observing that this limit defines f prime of 1, where f of x is 1 over x squared. Now, earlier in this lesson, we already did the work to find the derivative of 1 over x squared. We saw that it is -2 over x cubed. So f prime of -1, which is the value of the limit we're trying to find, is -2 over 1 cubed, and that's equal to -2. So we can conclude that the value of the limit in our question is -2. And we didn't actually have to do any of the complicated algebraic simplification required to find that limit just as a limit.